So as Siddharth said, this presentation is going to be about accelerating analytical engines using GPUs. So why do we need to do this? I mean, why should we accelerate databases? So database is a key technological component in any SaaS application stack. So monitoring and improving performance of database is absolutely important in order to ensure better customer experience so that we can increase our revenue. So this is absolutely important, and it becomes even more important when you have the breadth of applications that Zoho offers, say 50 and counting. So due to the breadth of the applications that we offer, we have the need for every single kind of database under the sun. Transactional databases, which are used in SaaS applications, analytical databases, which are used to process huge amounts of data to derive the insights from them to make business decisions, and graph databases, which are used to model connections and interactions between users in social media like Facebook and LinkedIn, and also to create knowledge graphs. And we have time series databases, which are optimized for storing and analyzing any data with a time value attached to it. Say, for example, monitoring data from IoT devices and logs which are generated by typical applications. Right. So how do we go about improving the performance of databases? So we're going to take a look at some of the basic steps that we can do. So the first thing would be creating indices on the columns if there aren't any indices already on the most frequently used columns, and normalizing and denormalizing the data as needed. The denormalizing part might come as a surprise to some of you, but it has certainly helped with performance, at least in some of the older database systems. And even in some non-standard engines, you need denormalization not to even feed data into them. The next step would be tuning the configurations provided by the database engine. Say it would be the amount of cache the database engine stores in the RAM. It could be the memory the database engine can use to execute a query, so on and so forth, many other things too. And we can also add a caching layer in front of our database so that we don't run the same query too many times. And we can also look at partitioning or sharding the data. This is still within the context of a single machine. So this cuts down the amount of data that the query engine has to process for a given query. So next would be, after we have tried all of what we have said before, we can upgrade the hardware, meaning move to a CPU with higher core counts so that we can process more queries or larger data sets. And we can increase the size of our RAM so that we hit the disks less often, so that most of the data can be cached in the RAM. And when we go to the disks, we can make sure that we use faster storage devices like NVMe SSDs, even multiple of them, so that we get back quickly when we go to the disks. And we can also move to workload specific engines like the one mentioned before, the time series engines or of the graph engines too. And the next step would be looking under the hood, taking understanding how the engine works, looking at each of the parts that are involved and trying to bring the maximum performance out of them. So once you tried all of this, the next one would be scaling out, meaning instead of looking at a single machine, we can deploy multiple machines in clusters to process queries or larger data sets. So we can optimize a particular engine, right? So which engine are we going to choose? Our choice was Postgres. The reason being, it is open source. It has been in development for, say, 2 decades now, perhaps even more than that. It has a really vibrant and strong community. It also has a favorable licensing terms. So Postgres allows us to extend the engine by modifying the behavior of certain components of the engine, say planner or executor, while being able to reuse all other parts untouched. And it is also being used for application teams. This means they don't have to learn a new database engine, adapt to its behavior, write new code to integrate it into their applications or tests and all of them. And it also allows them to reuse the tools that they have built for Postgres or the tools the community has built for Postgres too. All right. So Postgres is also the base for our other database R&D projects. So this presentation is about the analytical engine, and the list of engines that I mentioned earlier, we have projects going on all of it. And due to this allows us to learn from all of the teams, pick their brains apart. Say we get stuck in something, we could ask them for help, or we can even reuse the code that they've written in some of the places. Also, this provides some interesting integration opportunities. All right. So now we are going to take a look at a simplified representation of how a query is processed by a database engine. So once the query is received, it is then passed to the parser, which converts it into an internal representation, an abstract syntax tree, which is then fed to the planner, which determines the kind of operations and the order in which they need to be performed in order to generate the result. and then encodes them in a tree, which is then fed to the executor. The executor iterates the plan, goes through the plan, fetches data as needed from the storage engine, performs the operations that are defined in the plan, and then generates the result. Also, one more thing, if anyone has question at any point in time, please do let me know. I'll be glad to answer it. And the slide numbers are at the bottom right corner, so you can use them if you want to refer them in your questions. And I'm in full screen, so I won't be able to see any of the charts or anyone raising hands. Team from Amrita, please help me out with that.
Sure, sir.
Yeah. So moving on. So how do we accelerate the performance of databases in any way? So the performance or the speed of a particular query depends on three things. One would be the amount of data that we are going to process. And the next thing would be the kind of operations that we do on the data and how we do them, meaning how fast, how optimal are those operations. And the next thing would be the order of operations in which we do them. Because the order of operations can often influence the amount of data that is being processed at a given step. All right. So we already looked at three parts of the query engine, right? Please note that this is simplified representation. There are also other parts of a query engine, but we are going to look at just these three things because these influence the performance. The reason being, the storage engine provides the data that is going to be crunched. The executor does the actual operations, and the planner determines the order in which they are going to be performed. So these are the three modules we are going to focus on today. So we are going to take a look at some of the optimizations that a planner does in order to reduce the execution time. So one thing, take a look at the following query. So we have two tables, A and B. We are performing a join on them based on this condition, picking a column from each tables and doing a equality check on that. And based on that condition, we are going to extract two columns from that too. So the query is performing a join on two tables based on this given condition and applying a filter and then extracting these two columns from the final result. So the usual order of execution would be we read data from these two tables, perform the join that is specified, and then apply the filter condition, and then extract the columns that are necessary, say the X and Y columns from the table A and B. But instead of doing the join first, we could push the filter down before the join, because this would allow us to reduce the number of values from A which we use in the join. So filter push down really helps in a lot of cases where we can push down the filter. So if the filter, say for example, involves columns from both the tables, then that would not be possible. Since this filter only involves a column from a particular table, we can push this down before the join and reduce the number of rows that enters the join. So the next optimization is join reordering. So we have looked at the previous example, right? In this particular example, we only have two tables, so joining them is pretty straightforward. So consider an example where there are three tables to join, tables A, B, and C, and we're going to join B to A and the final result to C. So there are two options we can take here. Say we can first join A and C and join the result to B, or we can join A and B and join the result to C. So we need to choose the order which gives us the least number of rows at every step. So if A and B gives us lower number of rows, we need to do that first. Or if A and C gives us the lower number of rows, we join those first. So this is done with the help of statistics, because statistics are collected when insertions happen into a table, or we can do it as a standalone operation too. So usually statistics contain, say for example, for every column, the minimum and maximum values, the number of nulls in them, the most frequently occurring unique values, and say for example, an approximate count of the unique values too. So with these data, the planner can make an approximate decision when deciding when it comes to joining multiple tables. All right. So moving on, operation elimination. So we have looked at how to reduce the amount of data that enters in a particular stage. Also looked at doing operations in a different order. And now we are looking at a way to eliminate operations completely, if that can be done. Look at the example. This is the same query from the previous example. We are joining two tables on a particular column, applying a filter, and extracting a set of columns from the query. So say we have this min and max values for the column Y in our statistics. And based on those min and max values, we know for a fact that none of the values in table Y will be less than 20. See, all of them are 10, 15, and 19, etc. So in that case, no value will pass this filter and no value will come out of the join. As such, the result of the query will be entirely empty. We know that from the statistics we have upfront. So we can completely eliminate the query. We don't even have to run it. We can just return an empty result. So next step. So we have looked at some of the optimizations that can be done at the planner. Now we are going to take a look at some of the optimizations that can be done at the storage engine. So usually in a table where the data is stored in a row by row manner. So row one, which contains the, say, let's have 10 columns in our table. So row will contain column one, column two, column three, so on up to 10. So this is usually okay, but the problem is the queries that we run may not always use all the columns in the table. They may need only say 5 or 10 out of the 20 or so columns inside the tables, the actual tables. And the unit of I/O when it comes to database systems and the underlying storage devices are always in pages, not in a couple of bytes. So even when we ask for a couple of bytes, the operating system will return us a couple of kilobytes, and we just use a couple of bytes from those couple of kilobytes. That's how the operation usually goes. All right. So we have 20 columns in our table, and we only asking 5 of them to process our query. But since we can't read a couple of bytes directly from the disk, we have to fetch data in terms of pages. We'll get all the columns irrespective of whether we want it or not. So this is a significant wastage of resources, and we'll also end up spending a lot of time reading from the disk, and the disk is usually the slowest part of the system. Right. So how do we avoid this? So we can handle this by switching to a columnar form when storing data instead of the row by row form. So instead of, say, storing the first row, the second row, and the third row, we store values from the same column for all of the rows contiguously. So column 0 from row 1, column 1 from row 1, column 1 from row 2, column 1 from row 3, etc. So this will allow us to make better use of the data that is being fed to us. And this can also significantly cut down on the amount of I/O operations. Right. So the next step would be block skipping. So we do this by organizing the data into blocks of n rows. We already looked at the statistics wherein we have min and max values for the entire table. Instead of that, we go a little bit granular here, having min and max values for a set of blocks, for each block, for every column. So this metadata can also be used to filter out the blocks which are needed based on the filter condition. Say, for example, let's take this query for an example. So the filter condition here is if the value of column Y from table A is less than 20, then give those results to the join column, right? So to the join node. So say, for example, if the table contains 2 million rows and 1 million rows contain a value 10, and the rest of the 1 million rows contain a value 20, value 80, say, for example. Oh, no, something greater than 20. So 2 million rows in total, 1 million containing a value less than 20, and 1 million containing a value greater than 20. So in that case, we would still have to process the 1 million values because we can't eliminate the entire operation here. But if we store min and max values for every n rows, organizing the data in blocks, then we can eliminate the data contained in the first 1 million values because they are not going to be used anyway. So this can be used to granularly skip the blocks of data. We don't even have to read them from the disk. So this is another option of reducing the I/O overhead. So the next step is to compress the data. So even in row-based storage, the compression can help in reducing the data, but compression usually works by reducing the duplication present already in the data. So in a row-based engine, the probability of the same column occurring continuously usually is low. So you have a string type, an integer type, maybe a floating point type too. And since they are stored contiguously, we can compress the data effectively. But in a column store, since the values of the same column are stored together, the data type is the same, and it also allows us to compress the data really better. So we looked at 3 options to reduce the I/O overhead, which is switching to a column-based storage so that we can only read the columns that are necessary. Then storing min and max values for every n rows for blocks of data so that we can skip those blocks, skip reading those blocks, and then compressing the data so that when we read the data from the disk, we read a lesser amount of data. So in our production experience, some columns compress really well, other columns don't compress really well. That depends on the number of unique values present in them. On average, we could see up to 5x reduction on the size that is required to store a given data. All right. So there are also other layers in our particular engine. We are going to take a look at some of them. Right. So the first layer would be plan conversion. As we have already taken a look at, say, let me go to that again. So we have a parser, a planner, a parser which converts the query string into an internal representation, a planner which decides the order of operations and the kind of operations, the executor which actually does the operations, and the storage engine which feeds the data. So we could split these four engines, these four blocks into the front end and the back end. By front end, I mean the parser and the planner, and by back end, I mean the executor and the storage engine. Okay, coming back. So we didn't start a project by using Postgres. We started with a different front end, meaning the layers that can provide a parser and a planner. So we used a project called Apache Calcite. It is written in Java. And we later realized in conversation with our application teams that adapting to a completely different pathway than what they usually use is going to be difficult. So they wanted us to have our database engine based on Postgres so that they can integrate it really easily. So we switched to Postgres, and one of the reason being other R&D database teams also use Postgres, so we had to switch to that. And since we already used a different front end, we had code which integrated into that part of the engine. So we had a different plan structure than what Postgres provided us. So we had to create a conversion layer which allowed us to convert between the Postgres plan and our plan, our internal representation. And this also allows us to do some interesting things. Say, Postgres has been in development for over 2 decades, right? So with a couple of years of development, we would not be able to catch up to them in terms of feature compatibility. So there are always going to be some functions which we haven't ported to GPU yet. They can only run on the CPU, which means for some queries, the GPU can't run the query and the query needs to fall back to the CPU. So say we need some modifications in the plan tree and we do them to suit our needs. If the query has to fall back due to some reason, then the original executor, the Postgres executor, may not be able to handle that. And we don't want to be a bottleneck in that case. So we don't touch the original plan. And having a separate plan conversion layer allows us to make changes that are necessary to us. So we also have other layers like we mentioned earlier. One of this is a code generation layer. So the operations inside a database engine can be, compressed into basically three things. One would be the expression evaluation, which have something like, say, adding two columns A plus B, or applying a filter on some of the columns, or say, for example, concatenating the first name and last name to generate the full name. You get the idea. Expression, just expressions. So we generate C++ and CUDA code to handle these expressions on a query specific manner. And we need to generate C++ code because, as I already told you, some of the operations are not done on the GPU, specifically some string generating operations, because string generating operations need us to allocate memory on a per row basis. And memory allocation is a really expensive process, even on the CPUs where you have a couple of threads. And imagine how slow would that be when you have tens of thousands of threads, each competing for the same memory region. So we do allow some string generating operations, which are fairly trivial, not a lot of it. And the GPU has a really small stack space compared to the CPU. So any function with a deep call chain, say a function inside a function inside a function, or a function with a recursive function call, are typically computed on the CPU. So one other thing that we noticed in our experience is that code compilation by the CPU compiler is much faster than code compilation by the GPU compiler. This is probably because of the fact that the CPU has a lot of silicon area allocated to making our code run a lot faster. Say deeper pipelines, out of order execution, branch prediction, prefetching, SIMD, all of that. But the GPU has none of that. It instead trades all of the silicon area for a bunch of compute units, a bunch of add and multiplication units, if you will. So the GPU compiler is left to do a lot of heavy lifting that the CPU hardware would usually do. So the compilation takes longer. And it also is due to the fact that the GPU has a limited stack space. So the GPU compiler tries to aggressively inline every function that is present so that we don't actually generate call stacks, function stacks. Right. So in one particular example, a particular query from a customer ended up generating 2 million lines of code. The plan tree contained over 3,000 plan nodes. By plan node, I mean the operations that are the individual operations, say reading from the table, doing a join, a group by. Those are what we refer to as nodes. So the plan tree contained over 2,000 nodes. The code generated ended up being around 2 million lines, and it took 7 hours to compile. So we had to do certain techniques. We had to implement certain optimizations not to reduce the compilation time. Right. So one of the things that we do is we use precompiled headers. So precompiled headers allows you to compile some of the functions ahead of time and reuse them when we want to. So that significantly cut down on our compilation time. And we also have a code cache. So as I said earlier, we generate code for a given query based on the expressions that are in the query. So if the same query occurs again, instead of recompiling it, we just store it in the cache and reuse it. So the generated code is used as the key and the compiled binary is used as the value. And this is also compressed because the compiled binaries based on the expressions that are in the query often tend to be large. They can run into a couple of kilobytes and even megabytes. And when you have a millions of queries hitting us every day, if you don't compress, you'll quickly run out of memory, these things. And the code cache has a last recently used replacement policy so that we don't overflow the code cache. And one other thing we do to help with the code cache hits is we hoist the literals. Meaning, say, take this example. So we have an expression where we compare some column with a particular literal, 20 here. So if the literal changes, say to 30, if we could avoid recompiling this, then that would be really great, right? So what we do is instead of placing 20 in the actual generated code, we just place a placeholder, say a pointer to a particular integer. And then we fill the value to the pointer based on the expressions that we have. So even if the literals change in the expression tree, we don't have to recompile the expressions. All right. So now we are going to look at the executor part. So even though the GPU sits within the same system, it is in fact a separate computer, meaning it has to the data which the GPU processes needs to be present in the GPU's RAM, not in the CPU's RAM. So the GPU has a separate RAM. From where it accesses the data, it's going to process. So execution means we need to transfer the data from the CPU's RAM to the GPU's RAM. Only then we can start processing the data. So usually in the case of databases, we also have an extra step wherein we need to read the data from the disks too. Okay. So we have already talked about some of the techniques that we use in the storage engines to reduce the amount of data that we read, right? One is switching to a columnar storage engine. Two is storing min and max values for every end row so that we can skip the blocks based on the expressions that are present in the query tree. And the next thing would be compression, right? And there are certain things we do in the executor layer too to reduce the amount of data that we read. Again, one of them is late materialization, meaning, say, take this query for an example. We do join on two tables A and B based on a particular column, and then we select 5 columns each from each of these tables. So 6 columns from table A and 6 columns from table B. So the usual mode of operation would be read both of the 6 columns from each of these tables, so 12 columns, do the join, and then extract out the 10 columns, right? But we can do a small optimization here, which is the join can reduce the number of rows that come out of it based on the filter condition. So instead of reading all of the 10 columns that are necessary for the output, we just read the columns that are needed to perform the join in this stage. And once we cross the join, once we generate the output that are necessary, we can determine which blocks from the input we need to read based on the number of outputs that are generated in the join. So we can again reduce the number of rows, the amount of data that we read from the disk by cutting down the amount by only reading the columns that are necessary at a given stage. Because some of the operations in SQL have the tendency to cut down the input. All right. So the next thing is using pinned buffers to reach maximum transfer throughput. So I've already mentioned that the GPU is a separate computer, even though it sits within the same machine. And we have to transfer the data from the CPU's RAM to the GPU's RAM before we start processing it, right? So this transfer has to happen through some sort of a bus. And that bus is PCI Express. It's called PCI Express. So when transferring data through the PCI Express bus, there is one little thing that we need to notice, which is the transfers do not block the other operations that are scheduled in the CPU. So the transfers happen through a DMA engine, a direct memory access engine, which does the copy in the background. So in order for that to happen, the DMA engine needs access to the physical address of the memory region that we are copying. So usual memory provided by the operating system to us through the malloc or the new function calls are pageable memory, meaning the operating system can swap them out to the disk when the memory gets full. But we cannot allow that because the DMA engine is going to do the copy in the background, and the DMA engine needs the data that we are going to copy to be present in the RAM. So we need to ping the pages that we are going to copy by instructing the operating system, by letting it know that we are going to do a copy, and by stopping it from swapping out the pages. So that needs the physical address so that the copy can happen in the background and the OS doesn't swap it out. So in order to do this, we create pinned buffers, meaning memory that is allocated in the RAM and pinned to the RAM, instructing the OS not to swap them out. We can do that. There are function calls that allow us to do this. If we don't do that and we submit a pageable memory region to be copied to the GPU, the GPU driver allocates a pinned memory internally, copies the data from the pageable memory to pinned memory, and then initiates the transfer to the DMA engine. So we end up doing 2 copies. We don't want that. So we create pinned memories to reduce this double overhead. Right. So the next thing is NUMA pinning, again to speed up transfers in multi-socketed systems. So NUMA stands for non-unified memory access, meaning in a typical system, you have the CPU and then you have the RAM that is attached to the CPU, and then you have the storage system wherein you access the data that is going to be placed in the RAM to be processed, right? So what happens when we have a computational need that exceeds the capability of a single CPU? We go to multiple cores within the CPU. Yes, that can help to an extent. But what if we have a workload that is even bigger than what a single CPU can handle, even if it has multiple cores? So one way to handle that would be to use multiple machines to process that. Say, split the workload between 2 systems A and B, and then communicate whenever necessary to exchange the results. But that would be slower because we need to go through the Ethernet, right? So instead of doing that, what we can do is, instead of having a single CPU inside a single system, the manufacturers, the CPU designers, came up with the option of having multiple CPUs within the same system. See, please do note, this is not having multiple cores. That is still, that can happen, but this is in addition to that. So a single CPU right now does not have a single core, it has multiple cores. And within the single system, you can have multiple such CPUs. So this is what we refer to multi-socketed systems. So you typically can have anywhere between 2 to 8 CPUs within a single system in a multi-socketed system, and each of those CPUs can have multiple cores. So this allows you to handle much larger data sets or much larger computations without going out to a network system. So what happens is that each CPU has a RAM attached to it. So that is a particular memory domain. So when you have multiple CPUs within the same system, and each of the CPUs have a RAM attached to it, if the, say, CPU 1 needs to access the memory of the CPU 2, the request goes through a CPU interconnect, right? It differs based on the manufacturer. Intel calls it UPI, AMD calls it Infinity Fabric, and so on. But there is an interconnect that allows a CPU to access its neighbor's memory. Remember that, please. So this is called non-unified memory access. So it happens that we can have multiple GPUs within the same system too. It's not limited to just one. You can have 16 GPUs within the same system. So some of the GPUs can be connected to socket 1 and some of the GPUs can be connected to socket 2. And the operating system is free to schedule our CPU process, which communicates with the GPU, on a completely different NUMA domain than where the GPU is connected to. So say, for example, we have a bunch of GPUs connected to CPU 1 and a bunch of GPUs connected to CPU 2. Our process, which communicates with the GPU, could be scheduled on CPU 2, but the GPU could be actually connected to CPU 1. This means any copy from the CPU's RAM to the GPU now has to go through the inter-CPU interconnect, and that will also slow down our transfers. So what we have to do is, we need to make sure that the CPU process that communicates with our GPU and the GPU are actually on the same NUMA domain or on the same CPU socket, so that we don't cross the interconnects unnecessarily. All right. So the next step. So the data transfer actually has 3 stages, right? One is reading from the disk. Next is copying the data to the GPU. And the final step would be decompressing the data so that we can do any operation on it. So each of these operations can be done in parallel, meaning we can spin up a couple of threads on the CPU to read from the file. And we can, due to the DMA engine and the copy engine being in the GPU, we can do the data copy in parallel too. And the GPU, the compute engines are usually free to do any kind of operation while the data copy is happening. Of course, we can't do that on the data that is currently being copied, but we can do that on the data blocks that are already copied. So we have built a 3-stage pipeline, meaning we determine a block of data to read. We use a group of threads to read that, and then we move the data block to our copy stage, which will copy the data to the GPU memory. And then once that is done, we'll use our decompression engine to decompress it. So all of this can be done simultaneously, and we built a 3-stage pipeline to do that too. So we have talked about a lot of optimizations that we can do, say the columnar storage engine. the skipping blocks based on the min and max data, compressing data so that we don't read a lot of data from the disk, late materialization so that again we can avoid reading data that is unnecessarily needed, and then pinned buffers so that the operating system doesn't swap our memory out, or the GPU driver doesn't have to do an extra copy in order to do the data copy to the GPU, and NUMA pinning so that even if we are in a multi-socket system, we make sure that the communicating CPU process and the GPU are in the same NUMA domain so that we don't go through the CPU interconnect to do the memory copy. And then, of course, finally, pipeline decompression, meaning reading the data, copying the data, and doing decompression, all of them simultaneously. Even with all of these optimizations, the end-to-end time spent on executing a query is usually much larger compared to the actual execution of that query on the GPU. So the usual execution time is 25% of the end-to-end time. End-to-end meaning reading the data, copying it to the GPU, decompressing it, doing the actual operations, sending the result back. This is what I mean end-to-end. So the execution part, the actually doing the operation part, is usually 25% of the time. So we are being significantly bottlenecked by the data transfer and the decompression pipeline. So, and the copy, as I said earlier, happens through the PCI Express bus, which is really narrow compared to what kind of memory bandwidth the GPU offers. So typically, at least in a modern system, in a modern server system, the CPU has a memory bandwidth of about 500 gigabytes per second. The GPU has a memory bandwidth of about, say, a couple of terabytes per second. It is reaching close to 5, 6 now with the highest end GPUs. But the PCI Express bus, using which we copy the data from CPU to GPU, which is currently on PCI Express generation 5, can only do, say, 32 to 50 gigabytes per second in either direction. That's really small compared to the bandwidth that we have on either sides. So it's effectively like feeding a monster, the GPU, through a straw, the PCI Express. So our entire end-to-end time is completely dominated by the data transfer, despite all of these optimizations. Right. So we have looked at what we can do in the planner to cut down the data, to reorder it. Next, we have looked at the storage engine, the kind of optimizations that we can do. And we also looked at the other optimizations that we do in the executor layer. Now we are looking at some of the operations that we do. As I told earlier, the operations inside a database system can be simplified into 3 things. One would be expression evaluation. The next thing would be joining 2 tables. The next thing would be reordering them. Say, doing sort on the result of some particular node. So we are going to take a look at how we are doing sort. Now, for single column sorts, we use Thrust. Thrust is a library which provides a collection of GPU optimized algorithms. It is being developed and maintained by NVIDIA. So it contains multiple sorting algorithms, quite frankly. You have a comparison sort, which either uses a Pythonic sort or a quick sort underneath. You also have sorting that performs the operation using radic sort if the data types that we use allow it. So typically integer data types and to an extent floating point data types can be sorted using radic sort, and other sorts usually have to go through the quick sort or the Pythonic sort. And for multi-column sort, we have built a custom algorithm on top of the primitives that are offered by Thrust. So the algorithm that we use is inspired from LSB radic sort, the least significant radic sort. So the radic sort usually works by reordering the data by working on it a portion of a time, right? So say we have 10 digits in a particular data set where we are going to sort. The radic sort first works on a couple of digits, or maybe even 1 digit at a time, instead of looking at all of them. So we can think of multiple columns that we are processing in a query as a virtual number, and each of these columns as the digit of a particular number, of a virtual number. And we can apply the same techniques that the radic sort does in order to do our multi-column sort. Right. So the next thing would be string sort. We initially had a comparison-based sort, but the GPU is not really good at handling variable length data types, which strings are. If the length is fixed, then the GPU is really good, but variable length strings become the GPUs become a lot slower. So when our average length for a given string exceeded a couple of 100 bytes, the comparison sort that we used became much slower than the CPU-based multi-threaded sort. So we had to switch to a technique inspired from MSB radic sort, the most significant bit radic sort. So what we do here is first collect the first n bytes from each of those strings, do a sort, and then try to eliminate singletons. Singletons are strings that are unique, that don't have any other copies, or strings that have ended. Say, for example, strings that are shorter than other strings. Once you have done the elimination step, we can proceed to the next step, which is collect n bytes from the remaining strings, repeat the process again. So load n bytes, do the sort, eliminate singletons. This is the core compute step. We do this over and over again until we have no strings left. So join or group by can be done using two steps. One would be to sort the entire, say in case of group by, we can sort the input and then do a linear scan on top of it in order to figure out which of the two values are separate or they fall into the same bucket. And when it comes to hash table based approach, we just build a hash table based on the keys that are provided in the group by, so that we can do the aggregate operations that are specified on the query on them. And we can do the same thing when it comes to the join. We can build a hash table using one of the inputs involved in the join. Again, and we can use the other side to actually probe the hash table to build the output tuples. And when it comes to sort-based joins, we can sort both the sides and do binary search using one of the sides to figure out which tuples match. So that is how we do it. So here are some of the challenges that we faced and we still face now. As I mentioned earlier, the total execution time is a lot bigger, but the actual execution time, actual time spent on processing the data is usually 25% of the end-to-end time. So we spend most of the time on reading, transferring, and decompressing the data. This is due to the fact that we have a really slow interconnect, the PCI Express. So PCI Express has been improving. It has been doubling in bandwidth for every generation, but the movement between generations is taking a long time. Say PCI Express generation 3 came out somewhere in 2011, 2010, and Gen 4 came out fairly recently, around 2020. So the Gen 5 is available right now, but it is only available on really high-end GPUs like the H100 from NVIDIA, and these GPUs cost $20,000 each. So this will significantly shoot up our per machine cost, right? So we would, quite frankly, we have solved the problem of executing things on the GPU, but we still haven't solved the problem of moving data to the GPU faster, primarily because we are limited by the technology that is present. So CXL is a new and upcoming interconnect, and this is much better than PCI Express. It actually uses PCI Express underneath, but it also comes up with, it also gives us a couple of extras. Say, for example, the typical devices that are connected using PCI Express are your accelerators, say FPGAs, GPUs, and all that, and also storage engines. But the reason that we haven't used PCI Express to, say, connect RAM to a CPU is because the latency through PCI Express is really high. So individual request to it will take a really long time, and that is something the processing systems cannot handle. So we have used PCI Express as an interconnect only to connect co-processing systems like GPU and FPGAs, accelerators, and storage class devices. But when it comes to high-speed memory class devices, PCI Express falls behind. We can somewhat manage the bandwidth situation, but the latency PCI Express cannot handle. So CXL has provisions to allow really low latency between the communicating devices. And CXL also allows us to create a pool of memory that can be shared across multiple processors or accelerators. So CXL has a coherency provision too. Coherency meaning, since we have multiple accelerators accessing the same pool, there needs to be some kind of a protocol which determines the, say for example, the visibility of data to different processors, how updated the data is. One processor could be changing the data, and the other processor should not be reading a really older copy of it. So coherency allows us to share the same view of the data across processors, and CXL has a provision for that too. And due to the low latency nature, we hope that CXL improves transfers for really small data sizes too. So we said that bandwidth is really good with PCI Express and latency is really low, but this only applies for really large data sizes. I mean, 2 megabytes may not be really large, but when it comes to individual transfers, if we transfer a packet size of less than, say, a few hundred kilobytes, the PCI Express peak bandwidth cannot be reached at all. It, for whatever reason, is really cut down. Say we only get half of the bandwidth when we transfer really small packets. And due to the low latency nature, we also hope that CXL improves that. Okay. So next thing would be the limited RAM that the GPU has. So when we look at GPUs that cost less than $5,000, we only get a maximum 48 gigabytes for the past 3 generations of GPUs. Of course, the higher-end GPUs, which cost north of $20,000, like the H100, have over 100 gigabytes of RAM, but that's still really small when compared to the CPU that can get up to 4 terabytes in a single socket. So multi-socket systems can have much higher than that. So GDR6 is a variant of the RAM that is used in GPUs that has become a lot cheaper. So if the GPU manufacturers really like, they can give us much more memory, but they obviously won't do it, and in order to protect their profits and all that. So since CXL allows us to attach memory class devices to accelerators, we hope that in the future manufacturers come up with options to allow us to expand memory like we can do on the CPU sides through CXL. And if that is not possible, at the very least, if they allow us to directly attach SSDs to GPUs instead of going through the CPU, that would be really helpful too. There was actually a particular product that did this from AMD. It was called Radeon Pro SSD. Please look that up. So the next thing would be compression and decompression. We already told you that we compress the data so that we read less data from the disk, and we also transfer less data to the PCI Express bus. But the thing is, not all compression algorithms are really fast on the GPU. Techniques like run length encoding, delta packing, and bit packing, which are used to compress integer types, are really fast when it comes to decompression on the GPU side of things. But techniques like LZ4, Snappy, and Z standard, which are used for compressing strings, are really slow when it comes to decompressing on the GPU side of things. So even though we can, move the data faster, if the decompression ends up being slower, we can't move to the processing step quicker. So this has been changing. Say NVIDIA Blackwell is set to come up with the on-chip LZ4 decompression engine. This is a direct ASIC chip, and the benchmark numbers that they have shared, say, for example, they said that the GPU, this particular on-chip engine, can do up to 800 gigabytes per second of decompression bandwidth. So without this, currently we are only able to get around say 50 to 60 gigabytes per second. So that is a massive jump. But once again, if NVIDIA restricts this to only to the high-end GPUs which cost more than $20,000, then we are once again in a pickle. Right. So compression actually makes a really, really big difference. So this table shows some of the compression benchmarks that we did for particular types, say 3 columns from integer types and a couple of columns from double and string types. When the compression ratio is low, we can reach pretty good bandwidth. So let me give a base of where we are starting from. This is on a system that contains PCI Express Gen 4 interconnect, which has 32 gigabytes per second of transmission bandwidth in either direction. So 64 bidirectionally, but we are only going to look at the copy from CPU to GPU, so 32. But in practice, you can only achieve 20 to 24 gigabytes per second, somewhere around that, due to the encoding overhead of PCI Express. So for 24 gigabytes of practical bandwidth, we are able to achieve up to 120 gigabytes per second of end-to-end throughput. That's because we are able to compress really well and also be able to decompress really fast on the GPU for integer compression schemes. Say take a look at this particular example. In integer and in double precision, when we compress up to say 20x, we are able to exceed 100 gigabytes per second. But for strings where we use LZ4, even when we have 25x compression, we are not able to reach that. This is because the decompression part is really slow. And only when we reach around 50x compression, we are able to achieve over 100 gigabytes per second of total bandwidth. So, right. So we reached the end of the presentation. So I think we have looked at a lot of the techniques that we can use to optimize. So to quickly go through them, we can do some of the optimizations in the planner layer so that we can, reorder the operations, eliminate some of them, and reduce the amount of data that enters into a particular stage. And then we can do some of the optimizations on the storage engine by, say, switching from a row-based engine to a columnar engine, thereby reading only the columns that we need. Also, by storing metadata for every group of n rows called blocks, so that we can filter out the blocks so that we don't even need to read them based on the filter conditions that are available in the query. And of course, also by compressing data, whose effectiveness is absolutely increased by switching to a columnar format again. So by compressing and in practice, by actually achieving 5x compression, we are reading 5 times less data from the disk. So that helps. And the executor side of things, we are doing a lot of optimizations to avoid transferring or at least reduce the amount of data that you transfer to the GPU by using late materialization, meaning reading only the data that is necessary at a given step, hoping that the given step can reduce the number of rows that are needed for the next stage. And of course, we also have, say, GPU accelerated decompression, and we also have pinned buffers so that we don't do double copy through the GPU buffers. And we also have NUMA pinning so that in a multi-socket system, we don't go through the interconnect that thereby slowing down our copies. And we also spoken about the couple of optimizations that we do in our executor engine in order to process things faster. So to give you an idea of how much performance we can get out of this system, when we compare to a typical database system like Postgres, we get up to 50x speed up when we move to a GPU-based engine. So the speed up actually depends on the amount of data and the kind of operations that we do. So if you have a really small data set, say only a couple of gigabytes, it may not even make sense to move to a GPU-based engine. If you have a highly optimized CPU-based multi-threaded vectorized and columnar storage engine on the CPU side of things, you can get really good performance too. So if the data size is really small, say less than a couple of 100 gigabytes, it may make sense to stick to a CPU-based engine. Only when we cross a couple of 100 gigabytes or even reach into the terabytes when it comes to data sizes, it makes sense to come to a GPU-based engine and reap the performance benefit that comes with it too. Having said that, please do note, we are still limited by the PCI Express or any other interconnect that comes up. So we are waiting for the interconnect to improve so that we can truly unlock the maximum performance that is available on the GPU side of things. The compute is really fast. As I told you, the memory bandwidth situation is again 5 to 10 times higher than the CPU. So that alone would give us a 5 to 10x boost. But since we are moving data through a really narrow pipe, that is limiting the end-to-end performance that we get. All right. So that's it from my side. Time for questions.
You have a question in the chat.
Okay.
You want me to tell the question?
Can you explain
Hello,
a bit
am I
more on how
audible?
the column? Yeah, you're audible. I'm sorry. So I was reading the question.
Okay.
So yeah.
Okay.
So the question is, can you explain a bit more on how the columnar conversion helps optimization? So let me go back to the slide in case you want to look at it. Sorry, the storage, right? This one, yeah. So as I already mentioned, the data is stored in a typical engine in a row by row manner. So maybe I'll write this out. So my screen is still visible, right? Hello?
Yes, sir, it's visible.
Yes, sir, it is.
Yes, it's visible.
Okay, sure. Thank you. So let's say we have 5 columns in our table, right? Say we have an integer column, and then can I zoom this somehow? No, I'm not able to. So let me do something else. Okay. So let's say we have 5 columns in our table, right? An integer column followed by say a string column, and then followed by a double precision column. Again, some string column, okay, and some integer column again. So usually in a database system, the data is organized in terms of rows. So when the data is stored in the disk, first all the values in the first row is stored, then all the values in the second row, then all the values in the third row, and so on. So usually the table, the underlying table might contain more than 10 rows. In practice, we have seen up to 300 columns in a single table. But all of the queries that run on the tables might not use all of those 300 columns. Say the query might use only 5 or 10 columns in order to come up with the result. But there may still be 300 columns inside the table. In a row-based storage engine, what happens is that, say you want access to columns 1, 2, and 5, right? Since it is stored continuously, you have no way of skipping reading these 2 values too. So even though you only need columns 1, 2, and 5, you also end up reading columns 3 and 4, which are not needed at all, because they are stored continuously. Instead of this, if we switch to a column-based approach, wherein I've just stored a single row here, but assume that the first column has at least 10 rows, say for example. So this represents column 1 in a given row. This represents column 1 in row 2. This represents column 1 in row 3, and so on. So instead of storing it in a row-based form, by storing it in a column-based form, what we can do here is access just the columns that are necessary. Say we can access column 1 here, because the next value, which is going to be next to the first value, is always going to be from the same column. And we are going to use all of the columns, all of the values from the same column in a given query. So by storing in a row by row form, by storing in a column-based form instead of a row by row form, what we can do is we can avoid reading unnecessary columns. So say in a table with hundreds of columns, you only need 10 columns. In a row-based system, you would have no choice but to read all of the columns, because in order to access the later on columns, you can't skip reading these columns. But in a column-based system, the value next to the previous value is always from the same column, but from a different row. But we are going to look at all of the rows anyway. So reading or storing the data in this form allows us to avoid reading other columns, other unnecessary columns. So does that make sense? Please do let me know.
Participants can raise your hands or give your queries in chat window. Yes.
Sorry, I had some connectivity. That's why I couldn't respond earlier. But I have a follow-up question to what we were discussing with the column.
Okay. Please go ahead.
Yeah. When we say that it is easier for a person to, I mean, it's easier to gain this much information by identifying column 1, 3, 5, etc. Isn't it easier to just create a view that helps with that particular kind of access depending upon the role? Wouldn't that be?
No. Okay, please complete. Sorry for it.
No. Please go ahead, because I think.
Okay, so the view it's not a concrete thing. It's sort of like a placeholder in a way. So views don't actually move the data. A materialized view might help, but then again, creating a materialized view for every query might end up being a problem on its own. The thing with analytical database systems is that the queries are ad hoc, meaning you're exploring, you're trying to figure out insights from the data that you have. So the queries are not known upfront. So since we don't have idea about the queries that are going to occur, we don't know which columns are going to be used upfront at all. And say when you're exploring, you might have a question in your mind. You might run some queries to figure out the data, figure out the answers, and then you might have a different question based on the previous question. You might have a follow-up question, or you might have a question on a completely tangential line too. So when that happens, you go back and run a different query to figure out the answer for that. So the query patterns and the columns that are going to be used are not known upfront. That is the reason you can't extract out the columns.
Makes perfect sense. Thank you. That actually conveys quite a bit.
Yeah. What does X amount of compression int yield for? Okay, why does X amount of compression for int yield better gain as compared to the same amount of compression for string? Okay, so let me go back to that's a question that I was reading from someone. Okay, let me go back to the slides quickly. So this is the particular slide they are mentioning. The question here looks like, say, for a compression ratio of 20 for integer, we are able to get around 100 gigabytes per second. But for the same compression ratio on strings, we are only able to get 64. The reason being, the compression technique that is used is different for each of these types. For integers, it is, see, these types that we as we mentioned already. Because each of these algorithms, the run length encoding, the delta packing, and the bit packing, allow us to do things in parallel. But LZ4, Snappy, and Z standard, they are inherently serial algorithms. So the amount of parallelism that you can extract from GPUs is limited. So that is the reason we can't get the same amount of performance when it comes to strings, because the algorithm LZ4 that we use to compress strings is a serial algorithm. So the only parallelism that we extract from there is the number of blocks that we process in parallel. So the decompression stage is slower when compared to an integer decompression stage. So we only have limited performance when it comes to the end-to-end throughput.